Thank you very much. I would generally say wait to applaud after I finish the talk and you decide it's good, but I will take it. All right, so we're going to talk a little bit about model-based and data-driven methods for modeling and removing physiologically driven signals from both fluctuations. As a disclaimer, I'm not a person that likes to remove physiological fluctuation from bold data. I'm one of those people that like to use it and considers a little bit what's happening in the brain as a noise signal. But you know, whatever, it's good for you, it's good for you. So we're going to talk about it in a very neutral way. I might say noise, I might say signal, I might not say anything, and then you decide what you want to do with it. I want to throw a major acknowledgement to two people that contributed significantly to this presentation, Jingguani Chen and Cesar Caballero-Gaudes. What I mean by that is that half of the slide at the very least is theirs, and then I just basically managed to ruin them. So if you see that their work, congratulations to them. If you don't like them, it's my fault. And I'm going to try to give the talk that I normally do in 50 minutes in 35, so bear with me, I might go fast. As a disclaimer, I'm also a member of the PhysiPy community. Throughout the presentation, you will see code from the community toolboxes. That's not because that's the only option that is out there. There's many other options, for instance, Phys.io, the Phys.io toolbox from Tapas in MATLAB. AFNI has a lot of ways to model the physiological signals. This is just what I'm more aware of and familiar with, and so we can talk about it later if you want, but for the moment, it's that. So let's start with some impact. Why are we interested in the noise and physiological signal? Merrill explained us before why and how it can be interesting. But just as a quick recap on the physiology of the Bolt signal, and I'm very sorry for anybody that is not doing Bolt signal in this room. So the Bolt signal, if you remember how it's composed by different parts and different tasks. And by the way, I'm seeing people taking pictures. I'm going to put the slides on Slack later if you want to join that. So basically, there's different ways in which different organs can impact our Bolt signal directly. So for instance, the heart will impact the cerebral blood flow and the cerebral blood volume. The lungs, the respiration, the ventilation, the chest expansion will impact the cerebral blood flow again, the amount of oxygen in your blood. But also, if you're breathing consciously, the neural activity will show it as well. And finally, there's every other thing that basically impacts the autonomic nervous system that will also play a major role and impact, finally, throughout all of this chain on your Bolt signal. Okay. There's also another type of impact, and that's I think most of people consider noise, even people that use physiology in an informative way, and that's basically what are the shifts in the B0 field induced by ventilation or chest expansion. And basically what we see during scanner acquisition and data acquisition is that there's going to be mainly two ways this impact is going to show up. One is the phase image is going to change depending on the point of the respiration that we're measuring it at. The other thing is that there's going to be a decay, so basically a gradient moving from the chest out, and so basically there's going to be a decay according to the distance on the chest. And that's really important to know because that's something that might impact your data, especially if you have a cyclic task that is very synchronized to your breath. The impact difference on different scanners. So for instance, if you have different field strengths at 3 Tesla, 7 Tesla, 1.5 Tesla, it's going to change. At 7 Tesla, so the more the strength of the field, the more your physiological signal will be impacting your data compared to the just scanner noise and Gaussian noise and thermal noise. The voxel size will also impact it. Bigger voxels will have more physiological noise than thermal noise. The sequence and the TR will also be something that you have to take into account, where, for instance, different type of sequence, for instance, 3D or 2D API, will have different amounts of physiological data inside. The TR will also change the different proportions. And finally, the voxel position or the levels of analysis. We are thinking about the brain being unified and constant, But what happens actually is that some of the areas you might be interested in, some of your voxels are closer to the vascular system than others. And for instance, major veins, I'm talking major veins, not microvasculature. Microvasculature luckily is everywhere. But for instance, if you think about the sagittal sinus, or in any case, the visual cortex, they will be closer to areas where your signal will be impacted by changes in physiological system. And it's not just that. There's also other reasons for which we want to pay attention to systemic physiology, and we want to check what it's doing to neuronal states. For instance, task changes. So when your subject is in the scanner and it's doing something, you will see that the autonomic system change, you will see that the respiratory system change, you will see a lot of physiological responses that are very time-locked to your tasks. In this image, you can see, for instance, visual task paradigm, and I hope you can see it. How do I get the... No, I cannot. Okay. In gray, you see the moments of the visual task paradigm. What you see in black is the respiratory response that changes and increments while the task is active versus not. But if you just take the Human Connector project and you plot all of the basically all of the triggers of your tasks, and then you look at the respiratory volume over time, so again, respiration, ventilation, it will change in a very synchronous way. And so that's something that we have to take into account, because what we consider being cognition might actually not be related to cognition just alone itself. I'm not saying it's not completely, but partially it might be covered by other fluctuations. This physiological noise also changes in terms of denoising. So for instance, it might reveal differences in correlation within your voxels, or differences between subjects for which the inter-individual differences and inter-individual variability might increase if you don't do physiological denoising. How do we do physiological denoising? I'm going to talk a little bit about model-based in this moment. So if you are acquiring this type of data, later we're going to talk about what to do when you're not acquiring this type of data. But let's start with these corrections. So first of all, we just talked about how ventilation changes your B0 shifts and B0 signal. One thing that we can do is the retrospective image corrections, and that's basically a way to take into account those changes and those shifts in your respiration and in your cardiac signal. And what you do is basically just you're going to compute a Fourier series expanded in terms of cardiac and respiratory phases. It sounds very complex. It's just basically a bunch of sines and cosines that you can quickly and easily compute. You want to perform that at the very beginning of your preprocessing. And that's because the moment you apply a temporal or spatial transformation, so for instance, slice correction, motion correction, anything else, that link between the voxel position and the Fourier series will change. And so your regressor will not be correct anymore compared to the space where they should. This is really time-locked to not only to the TR, to the temporal series, but also to the slice timing correction. And as I was saying before, it's an expanding order. So basically, you can choose how many orders do you want. Every time that you want to expand, you can. It's just complex in the terms of understanding how much to collect and how much to expand your order selection. Commonly, what we do is we select 2 or more orders, which means basically four regressors per voxel. But you might want to have more orders. We see normally that there's a decaying amount of variance explained in the data the more we increase the amount of orders. And every time that you add an order, again, you're adding 2 regressors. So 2 regressors for respiration, 2 regressors for cardiac. We're already talking about 4 regressors at the first order, 8 at the second. But you might also want to do some multiplicative Fourier terms that are very impactful in especially subcortical areas, and that adds another 4 regressors at every order. If you add too many orders, you might understand that the degrees of freedom that you're working with might reduce very quickly, and it might not be convenient later in time. So there's always, you have to pay attention to the trade-off between the variance explained and the variance that you're removing in terms of noise and the degrees of freedom that you're removing. Now, for everything else, when it's just about modeling physiological changes, if you're one of those people that are working with very fast acquisitions, very fast TR, so for instance, if you're doing FNIRS, or if you're using fast MRI or MR encephalography, you might be able to see the signal itself in your data. And so basically just a notch filter will be able to find the respiration, the cardiac system, and all of the other slow frequency fluctuations that you might want to remove. But unfortunately, what we normally do in fMRI is not having those ultra-fast TRs. Most of the time what we see is that there's going to be a couple of peaks that we have to take into account. So for instance, we have cardiac peaks at around 1.4, 1.5 hertz, and then again between 0.8 and 1 hertz. That's a very annoying moment to be, because normally our TR is around that area. And finally, the respiration will be around 0.33 hertz, and that's a bit less, so it's easier to find. But what happens is that, for instance, if you have a TR of 2 milliseconds, sorry, or 2,000 milliseconds, or 2 seconds, by the Nyquist frequency terms and by the frequency rules, our frequencies, to a certain extent, will be sent back and aliased in the areas of the frequency domain, of the spectral domain that we are interested in, because we interpret it as bold signals coming from cognition. And so those low physiological changes that are related to heart rate variability, respiration depth and volume, and other types of information is what you want to pay attention to, particularly if you work with bold MRI. So let's look at them very quickly. One of them is the respiratory variance per time, and actually the author of this model is here in the room, so I'm going to become very nervous in this moment. So the RVT, respiratory variance per time, is the ratio between signal amplitude and period, which means what we are looking at is basically the peaks and the troughs of our signal. That means that it requires peak detection, so that's something that you have to add to your preprocessing of the data. And the important aspect of the signal that you want to pay attention to is the amplitude and the peak distance. So if you see moments in which your time series is very flat or very big compared to the rest, that might be noise you have to pay attention if you want to use it for your RVT composition. Because of that, it's very sensitive to abrupt changes and noise. So if you want to be sensitive to that, that's great. If you don't want to do that, there's other options. One other option is the respiratory variation, and that came into the literature for 2 reasons. The first one is that it's very easy to compute. It's just the standard deviation of the amplitude in a sliding window. It's the amplitude of your ventilation, so basically the chest belt expansion. It does not require peak detection, so that's something that you don't have to worry about. The important aspect so becomes just the amplitude itself. So again, if you have noise in that signal, so for instance, if your subject is moving, that's something that you might not be able to use. But it is less sensitive to noise than RVT, and so it might be easier to use compared to RVT. The only problem that it has is that you must define the sliding window length. Traditionally, in our literature, the sliding window length is 6 seconds. Why? I have the feeling it's because it was basically DTR before and after the central point in the original paper in which this was proposed, and with a TR of 2 seconds, that makes 6 seconds. In general, it's good to think about the fact that your respiration is basically 3 second cycles, and so that represents 2 cycles. But you might want to increase it to be less impacted by noise, or in any case, more smooth in your data. If you are working with respiration like I am, then you're interested in CO2 and what CO2 can do. You can see here, for instance, an example of a breath hold task, where basically we ask our subject to hold their breath for 10-20 seconds to measure cerebrovascular activity. In blue, you see the respiration itself, so the amount of CO2 that we collect through the cannula. In orange, you see the end tidal CO2. So what we use is basically the pressure of end-tidal CO2. That's a measurement that is approximation for the arterial pressure of CO2, and that's what we are actually interested in, because that is going to tell us how it changes, how it impacts the vascular system. Unfortunately, as Mirov was explaining before, that's very invasive, so we want to avoid that. So expired gases is what we're working with. To compute it, it's literally just the linear interpolation of end-tidal peaks, so it's fairly easy to find. It requires peak detection. And the important aspect of the signal are, once again, amplitude and peak detection. So that's something that you have to pay attention to when you acquire your data. If they're not good, don't use them. One thing to pay attention is this. When we think about PPG, ECG, cardiac expansion measured through, for instance, a belt, that's a digital signal. That means that as soon as something happens, well, more or less as soon as something happens, minus a very, very small latency, your signal is going to be acquired. In this case, because it's gas, it's an analogical signal. And normally your sampler, basically the instrument that measures the gas fluctuations, it's very far away from the scanner because it's normally in another room. And so you have to take into account basically those 2-3 meters of tubes that the gases have to go through. And that means that there's a huge latency between what happens in your body and in your vascular system in your brain compared to what you're seeing. And so that's something that you might want to pay attention to and take into account and correct for. Let's move to the heart. How do we measure the heart? We can use heart or pulse rate variability, depending if you're using an ECG or a PPG, and the heartbeat intervals. And that basically, both are measures of the distance between the peaks of your cardiac signal in a sliding window, once again. It does require peak detection, and the important aspect of the signal is the peak position, which is a good news because, for instance, it means that if a subject is moving their finger and probably the amplitude of the signal is not that good, if the peaks are still where they should be, you can still use the part of the data that is affected by motion. The problem, again, is defining the sliding window length. In our literature, is once again 6 seconds, because that's about 3 to 6 cardiac cycles. Unfortunately, if you go into the literature of physiology, and for instance, physiology monitoring systems like watches, they will tell you that under 40 seconds, that's not a good HRV measurement. Now, under 40 seconds for us in fMRI, when our normal acquisition time is 10 minutes, might be a bit too much of a big window, but you have to take into account, once again, how the signal looks like and how much you want to be sensitive to noise. Now, all of these fluctuations is what we call slow, bold physiological fluctuations models. You will model them as nuisance regressors. Well, you will model them as regressors, and those are the responses that we've seen so far. But what happens is that as you create a convolution of your task model, you want to create a convolution of this model as well. And the canonical physiological response functions are different from the HRV. From the HLF. And so they are described in the literature. You will find this model both in code and in temporal points online. But basically, if you're working with RVT or respiratory variation, you might want to use the respiratory responses. If you work with the heart rate, you might want to use a cardiac response. And if you're using a gas challenge, so the pressure of entitled CO2, you might want to use the pressure of entitled CO2 response. Some people suggest not to do that, so it's always interesting to look at the impact of your models before convolution and after convolution and decide which one to use depending on the interpretation that you want to do on the data. Now, you might think, oh, then that's easy, I can just do that, that's fantastic. I would say, yes, you can, and that's the basis. It's already very good to do, and it's very good to either model your physiological responses or do denoising, but the truth is that it's a bit more complicated than that because all of the latency that I was talking about before, it's present also in your brain. And so you will have a lot of regional variability in the responses in which, for instance, you might have an optimal latency of respiratory responses, but because, again, we're talking about signal that travels through vessels, because of the heterogeneous vascular anatomy, you will see differences in the regional bold physiological responses, which is why somebody suggests not to use them. Okay, let's say that I forgot to turn on the biopack or the ADI instrument or whatever else I have in my scanner to measure physiological data. Or I'm working with data from colleagues or from open data sets that do not have this type of data. What can I do? There's a couple of things you can do, even in that case. The first one is just using principal component analysis. There's a technique called CompCore that's very well implemented in AFNI, for instance, and that's basically computing the principal component analysis in order to explain the highest variance from voxels from either anatomical landmarks, so for instance the white matter or the CSF, or from the voxel with the largest temporal standard deviation. If you do that, you might see some differences in the first principal components, and if you plot the frequencies of those principal components, you will see that some of them correspond to the cardiac and the respiratory variation. The CSF, because of the pulsations that we talked about before, the Monro-Kelly doctrine, will present cardiac and respiratory responses. The white matter normally contains more of the respiratory responses. And normally the questions is always, how many principal components do I choose? That's still an open question. If you have the answer, please tell me. I would like to know. But it's normally either a fixed number or it's based on a percentage of explained variance. And the fixed number is always 5, because 5 is a nice number. What can you do if you don't want to use PCA? Normally, one thing that you might run anyway in your pipeline is ICA, independent component analysis. For those of you that are not aware of that is, just go check the FSL documentation. It's great, but very quickly, you're basically taking your signals and then you're using ICA to split them into 2 matrices, one representing spatial components and one representing temporal components. And if you start plotting them on the brain, and if you start plotting them and visualizing them, you can see many different aspects of physiological changes and physiological impacts has on your ball data. So for instance, you will see large veins that look more or less like this. It's very clear in the spatial component because it's going to be around the sagittal sinus. You will see cardiac pulsations. That comes a bit more clear in terms of landmark because it's closer to the circle of Willis, but also on the frequency domain, on the spectral domain, you will see basically the moment in which the spectral fluctuation should be. And you will also see CSF fluctuations, CSF pulsations that still contains that cardiac rhythm, but will also be more spatially localized around the ventricles. Now, if you do want to know more about this independent component analysis and have a guide on how to basically classify them, there's a fantastic paper from Ludovica Grifanting from 2017. I always refer people to that paper because it contains a fantastic explanation of how the signals and the components should look like. Now, what we normally do in fMRI, it's not what you do in FNIRS or it's not what you do in EEG. What we normally run is spatial ICA. That's because of methodological constraints. And that's unfortunate because by definition, it cannot, like spatial ICA cannot isolate global effects. And so, for instance, widespread respiratory effects will not be picked up by the components. Temporal ICA, on the other hand, is what would be able to capture those changes, but it requires a large number, of samples in time in order to overcome the fact that they have to be incredibly higher in terms of samples than the spatial samples. So one way that was suggested to overcome this limitation was basically to run spatial ICA first, and then in the spatial ICA, if we still have a TR that is fairly fast, just take the voxel of each component in the spatial ICA, run a temporal ICA on top of that, very similar to what EEG people are doing, and then basically manage to find the signal sources in those models and then bring them back together in order to find possibly cardiac, respiratory, or even arousal and other type of signals. Now, that's not the only thing that you can do. I'm just going to mention this other option because I think it's fairly smart. So let's say that you did not acquire cardiac signals. What can you do? Okay, so just take your sequence, your fMRI Bolt sequence, and if you are using a multi-slice acquisition sequence, you will be able to see all of the signal averages across all of your times. And so, for instance, that's the idea there. Now, if you take those time series, and then you correct for the slice acquisition period. So it's basically what you would do in a slice realignment. You will see that they start shifting. And if you start paying attention to all of those time points, and if you compare the temporal lag together with the position of the slice, you might start to see that if you pull them together, the time series that you can trace is this one. And that one looks fairly familiar to physiological people because that's the PPG. It's not the PPG per se, It's something that looks like the PPG. In fact, it has a very good correlation with the PPG itself. But if you run a convolutional neural network filter on that signal, you will be able to increase even more the correlation with PPG signals. Now, obviously, remember that this is not real signals. So if you're using them for denoising or plotting or modeling, remember to pay attention to the variance that they explain. How do we do this demodeling, or how do we do this denoising? That's very easy. We just use a GLM, as we would do with a task. And what we want to do is basically just combining all of the models together, possibly running everything in one step. So, for instance, at the end of your preprocessing, if you're running resting state analysis, or together with your task analysis, just add them as nuisance regressors. Just pay attention on how they impact each other. And so, for instance, it's very good to just check if you have a lot of variance explained by, for instance, ComCore, to check that that variance is taken away from respiration. Normally we do the opposite. Or maybe your respiratory belt might be picking up some cardiac fluctuations as well. And so checking that the models are, for instance, orthogonalized is a nice way to be sure that you're not impacting your signal too much in a way that is actually throwing off your basically the regressor of interest of the data of interest that you have. And the other thing you can do is also checking how aggressive your denoising is if you're doing denoising. And so if you do have a task that you're interested in, you can just basically model that task and then orthogonalize all of your nuisance regressors to that task. That's something that we never think of when we do, for instance, motion regression. But that's something that we can do, and it's important to do, especially in physiology, because we're never sure of what we're looking at. So to sum up, very quickly, we talked about the fact that part of the bold signal is characterized by physiological changes. There's changes in the B0 field, that's definitely noise. There's physiological signals per se, if you're having an acquisition with a fairly fast TR. There's also aliasing of the physiological signals in the TR range, if you're having a TR that is a bit sluggier, a bit longer in time. The impact of physiological fluctuations depends on multiple factors. For instance, where you are in terms of space in the brain. For instance, where that voxel is compared to the vasculature. For instance, many other reasons. The other thing is that we can acquire physiological data in order to use the physiological data to create models to either map these physiological changes or just to denoise those physiological changes from the bold acquisition if we are interested in cognition and cognitive activity. Those models are basically retroicor or slower changes models, so RVT, RV, HRV, BRV. And those are the best models. Those are the best ways in which you can do denoising or physiological imaging. However, if you don't have available that type of data, you can still get an idea of what the physiological changes and physiological fluctuations will look like in your data just by using signal decompositions methods such as PCA or ICA or other deep learning models. That's all for all. That's all for me. It's not all for this educational course. If you have any questions, I will take them now.
Okay, just a little reminder, you can do it online through ohbm.cnf.io or come to the front if you have any questions. We already have a question online. What if the physiological signal covariate out is correlated with the cognitive function of interest? Would this be a problem?
Yes, it is a problem, definitely, because basically what you're mapping and what you think you're measuring and modeling as cognitive response might be actually physiological in nature. And so that's what, for instance, like what I showed you before, what happens when you have a task that is very time-locked to your respiratory function and respiratory fluctuations. But once again, if you want to be sure, well, you're never sure, actually. But if you want to be slightly more sure that what you're measuring and what you're mapping and what you're interpreting is cognitive in nature, an orthogonalization of your physiological regressors is what I would suggest. So that you are removing physiological fluctuations and you can look on about, like, basically you can try to assume that your task is respected in terms of variance. I hope that will answer the question. I hope that that's answering the questions. I'm normally better answering the question while I'm here. If I'm not doing that, please come to me after in the break or during OHBM. I will try to catch you as well if I see you, but please do that. Yeah.
Okay. Oh, I see there's 2 questions.
So if I understood it correctly, you said that we should get rid of the physiological data before doing any pre-processing. Is that right?
No. Yes and no, sorry. So basically what I meant is there's 2 types of physiological effects, right? So the first one is the physiological effects on your magnetic field. And that is, for instance, what is modeled by retro-K-core or retro-I-core, which was the first thing that I presented. And that's where you want to do it at the very beginning of your preprocessing, because your preprocessing will change, like retro-K-core was born to be modeled in the K-space, which is something that normally we don't see as users of neuroimaging. Retro-I-core came right after because it was easier to implement on magnitude images. But the problem is that it's very specific to the slice. And so as soon as you do a slice time realignment or a motion, basically motion realignment, you're disrupting the link between the retro-I-core regressor and your slice and the position of your voxel. And so that's why I suggest to do it at the very beginning. Everything else should be done at the end. So at the very end of your preprocessing, after you did everything, like after you did spatial realignment, temporal filtering, if you're doing that, should be considered very well and possibly done again together with the regressor, with the nuisance regression, but sometimes you might end up doing it before. You just have to pay attention to the fact that if you're filtering your data, you have to filter also your nuisance regressions, your nuisance regressors. But normally what I would do is do everything at the very end, if I'm doing resting state, or I will model everything together with my task of interest if I'm doing a task-based analysis. And I'm very sorry if that was not clear before.
Okay, very nice, thank you. And what about task-based connectivity, like psychophysiological interaction? Because then we can either denoise the data like in functional fMRI, so like before modeling, but we can also use it inside the models, the regressors. So what would you suggest?
I'm always a little bit amused by the fact that psychophysiological interaction do not contain physiological data. But I would add them there, actually, because at the end of the day, psychophysiological interactions are a task model. The tricky part is that the physiological part of your psychophysiological interaction is the ball signal, right? And so you might want to do the physiological denoising on that regressor, and then add everything else inside the model of the PPI.
Thank you.
But just to be clear, I don't think there's literature that shows how to do it. Like that's my 2 cents and my interpretation. I'm not sure there's a specific manual on that.
Thank you for the talk. And I actually struggle quite a bit in the physiological noise correction. And if we buy the argument that a part of the physiological fluctuation is the signal but not the noise, and a part of it is definitely noise, and what do you think of the clue that will allow us to separate the signal versus the noise component? One thing I've been thinking about is the latency. I look at the end-tidal CO2 response function that seems to be delayed a little bit more than the respiratory and the cardiac response function. And the hemodynamic response function maybe have a little bit different latency and a little bit different regional distinctions in the latency. So I want to take, what's your thought and advice?
Thank you very much for the question. I completely agree with you. It's a bit complicated. So I would say we can agree on the fact that changes in our data that are not seen in the setup in the brain itself, we can interpret them as noise. I think we can all agree on that, at least in this audience. There's somebody that would consider that signal as well, but at least in this audience, we can talk about noise. And so, for instance, once again, the bit zero shifts that comes from respiration and cardiac systems, I would treat them as noise. Now, how that affects, for instance, when you're doing a breath hold scan or a CO2 gas challenge, unclear. And so it's very important to pay attention there as well. What I would normally suggest is to orthogonalize the retroichor components to your task, just to be sure that you're not removing your task at the very end. But what I meant by noise or signal is mainly the fact that if you're measuring cognition, then physiological signals are noise. If you're measuring physiological responses, those are the signal of interest. With one possible exception, that's when you're doing affective neuroscience, because then depending on the interpretation that you want to do in terms of what your emotional responses is, whether you want an emotional responses that consider the physiological changes related to the emotion, or you would just want to take into account the cognitive response of the emotion, you will change the way you would treat your physiological data in terms of noise or not. That's a completely different panel discussion. That's probably even a completely educational course. I'm not an expert in that. I just managed to work with these people, the people that work in affective neuroscience. Lovely to have a chat if you want to, but for the moment, I will not do it. In terms of doing physiological imaging, so for instance, CO2, your gut's interpretation of the latency is also what I follow, and so normally because CO2 changes will be very specific voxel-wise in terms of latency. When you apply, for instance, lag regressions types of model or phase-based models in order to image, like basically in order to estimate the impact of ATSO2 changes, there you will see other type of physiological responses or even the motion that is related to the discomfort in CO2 if you're doing a CO2 gas challenge or in the breath holding. That will be either instantaneous or will happen at a very different latency compared to your ATCO2 impact. And so once again, when I do that, I do orthogonalize everything to my task of interest beside the motion. And that's the suggestion that I will give. It's always interesting to also look at the variance that they're explaining, and especially if the variance of the residuals. And if the residuals look like something that should be the task that you're interested in, then obviously there's something wrong there. But it's all about looking at the data and understanding how you want to interpret your data as well.
Okay, there are quite some more questions in online, but I will do one quick question before the break. Could you tell us what is the advantage of convolution of physiological signals with the HRF?
Good question. So if I understand correctly, and I'm going to wait for a nod in the audience, you're talking about, for instance, convolving RVT with HRF. Do I understand the question? I am going to interpret it like that, and if that's not the case, please come to the break to talk with me. I understood the question? I think so.
I think so too.
I think so, yeah, okay. So I'm going to be very honest. When I do PET-CO2 modeling, I normally use the HRF rather than the ET-CO2 response, but I know that that's partial, like it's considered by some people in the field of physiology wrong, because the HRF is the bold signal response to a cognitive task. It's the bold signal response to basically what you envision being the neurovascular coupling. Physiological challenges, physiological changes are not modeled by the neurovascular coupling. They are different types of coupling with your bold signal. And so when I do RVT, for instance, I would not even convolve with the respiratory response function, but you might want to do it, especially if you're doing RVT or RV or other type of signals that are otherwise not smooth enough to explain the bold signals. So I know it's complicated, but try to use the right response functions if you're modeling the right thing. Again, some people in the physiological field will tell you that these response functions will still change the relationship between the physiological responses that you're looking at, especially when you're doing PET-CO2, and your blood signal in a way that is wrong and nonlinear. So you always might want to check how your estimations look like if you're not doing convolution or if you are.
Okay, then one of the other questions we had, if it was possible to put the QR code on. We will do this during the break, so if you want to join the Slack, you can do this using the QR that we will put up. But for now, please join me in thanking Stefano again for his great talk.